This is section 1.3, Inverse Exponential and Logarithmic Functions. We will start with exponential functions. An exponential function has the form f of x equals b to the power of x. Notice that the variable x is located in the exponent, and the domain of this function is any number from negative infinity to positive infinity. This means that in place of x, we can use any real number. The base is a constant number b, and this number has restrictions. The restrictions are that b has to be positive and b cannot be equal to 1. If we would allow b to be negative or 0, then in place of x, we would not be able to use any real number. For example, if we would have the function f of x equals, and the base would be a negative number, for example, negative 4, and let's say that in place of x we want to use the fraction 1 over 2, then we can write this as square root of negative 4, but square root of negative 4 is not a real number. In place of b, we cannot use 0 either, because if we would have f of x equals 0 and then the exponent is also 0, then this expression is undefined. Also, in place of b, we cannot use 1 because 1 to any exponent is still 1. And if the outcome is always 1, then we have a constant function, not an exponential function. So if these cases don't work, then let's see some examples of exponential functions. One can be f of x equals positive 3 to the power of x. As we see, the exponent is a positive number. We can also have the function f of x equals negative 3 to the power of x. But we can't have f of x equals negative 3 to the power of x. So do you see the difference between these two functions? Here the base is negative and we cannot have a negative base, but above we have a negative in front of 3 to the power of x. So we can say that this is a variation of a basic exponential function. Now we talked about the domain of the exponential function, and we said that in place of x we can use any number from negative infinity to positive infinity, but now let's talk about the range. The range, which is represented by f of x, is any positive number. This means that if in a function we replace x with any number positive, negative, or 0, the result will always be positive. For example, if in the function f of x equals 3 to the power of x, we replace x with a positive number, for example 3 to the power of 2, the result will be positive. If we replace x with 0, 3 to the power of 0 is 1. And if we replace x with a negative number, for example, negative 2, 3 to negative 2 means 1 over 3 to positive 2, which is positive 1 over 9. So do you see how no matter what we use in place of x, the result is always positive? So again, we have that the domain of a basic exponential function is any number from negative infinity to positive infinity, and the range is any number greater than 0. Now let's talk more about the base. We said that the base cannot be equal to 1, but if the base is a number that is greater than 1, then the function will be an increasing function. Let's create a table of values and graph the function f of x equals 3 to the power of x. Here we have the table, and in place of x I will use the numbers negative 2, negative 1, 0, 1, and 2. Then 3 to the power of negative 2, which equals to 1 over 3 to positive 2, equals 1 over 9. 3 to negative 1 will be 1 over 3. 3 to the power of 0 will be 1, 3 to the power of 1 is 3, and 3 to the power of 2 will be 9. Let's have the rectangular coordinate system, and then we will make the graph. The first point is negative 2, 1 over 9, then negative 1, 1 over 3, 0, 1, 1 to the right and 3 up, and 2 to the right and 9 up. Now we will connect the points and get the graph. As you see, this is an increasing function because as we move from left to right, the graph goes up. Also, this graph stretches to the left and to the right indefinitely, and this means that the domain is any number from negative infinity to positive infinity. However, this graph stays above the x-axis. That's why the range is any number after 0. Now, let's graph the function f of x equals 1 over 3 to the power of x. So, if to the left we had a function whose base is greater than 1, now we have a function whose base is less than 1. If the base is a number between 0 and 1, then the function is a decreasing function. Let's construct the graph. Here we have the table, and in place of x we will use again -2, -1, 0, 1, and 2. When x is -2, then 1 over 3 to the power of -2 will make 9. And that is because 1 over 3 to the power of -2 equals 3 over 1 to the power of +2, which makes 9. So you see that if we have a fraction raised to a negative exponent and we flip the fraction, the exponent becomes positive. So let's write 9 in the table, and the same will be in the second row. 1 over 3 to the power of -1 equals 3 over 1 to +1, which is 3. So let's write 3 in the table. Then 1 over 3 to the power of 0 is 1, 1 over 3 to the power of 1 is 1 over 3, and 1 over 3 to the power of 2 is 1 over 9. Now let's create the graph. The first point is -2, 9, then -1, 3, then 0, 1, then 1, 1/3, then 2, 1/9. Now we will connect the points and we will get the graph. You see that when we move from left to right, the function is decreasing. Also, it is important to mention that both graphs cross the y-axis at 1. As you see, in both tables we have the point 0, 1. Now let's talk about the natural exponential function. The natural exponential function is f of x equals e to the power of x. As you see, this function has a special base e, and this number is an irrational number that is approximately 2.7. Because the base is a number that is more than 1, this function is an increasing function. Now, what is interesting about the natural exponential function is that this is the only function with the property that if we have a tangent line at the point x equals 0, then this tangent line will have the slope 1. Now, let's talk about the inverse functions. The definition tells us that if given a function f, its inverse, if it exists, is a function f inverse such that whenever y equals f of x, then f inverse of y equals x. To understand what inverse functions are, let's take an example of a function and find its inverse. Let's say we have the following function, f of x equals 2x plus 5. To make the steps easier, we will replace f of x with y. So we will write y equals 2x plus 5. Now in the next step we will find the inverse function, and we will do that by interchanging x and y. So in place of y we will write x, and in place of x we will write y. And this is the inverse function, and now we just have to solve it for y. If we subtract 5 on both sides, we will get x minus 5 equals 2y. Then we will divide both sides by 2, and we will get that y equals x minus 5 over 2. And now to show that this function is the inverse of this one, we will use the notation f inverse of x equals x minus 5 over 2. Now, there are a few properties we need to understand about inverse functions. If we have two functions, one of them being f of x and the other one being f inverse of x, then the composition of f inverse of x equals x, and the composition of f inverse of f of x also equals x. Let's use the examples we had above to see if we perform the composition, we will get x in each case. The first function, f of x, was 2x plus 5, and the second function, which is the inverse of the first one, is x minus 5 over 2. First, let's perform f of f inverse of x. What we see here is that f is the main function and f inverse is the domain of f. This means that in this main function we will replace x with x minus 5 over 2. So let's bring 2 down, and then in place of x we will have x minus 5 over 2. Then we will bring down 5. Here 2 and 2 will cancel. Then x minus 5 plus 5 will cancel 5 and negative 5, and the result will be x. So we see here that the composition of these two functions gives us x. Next, we will see if this is true. There we have f inverse first, and then f of x. So f inverse is the main function, and f of x is the domain of f inverse. And what this means is that in this function, we will replace this x with 2x plus 5. So here we will have 2x plus 5, then minus 5, then over 2. So let's start a fraction bar, and in place of x we will write 2x plus 5, then minus 5, then over 2. 5 and 5 will cancel, then we will bring down 2x over 2, 2 and 2 will cancel, and the result will be x. As you see, indeed, the composition of f inverse and f also gives us x. Another interesting thing about inverse functions is that they are symmetric with respect to the line y equals x. Let's see what this means by graphing the functions we had above. The first function was f of x equals 2x plus 5. We will graph it using the slope and the y-intercept, and the slope is 2 and the y-intercept is 5. The inverse function was f inverse of x equals x minus 5 over 2. We can also rewrite that as 1 over 2 x minus 5 over 2. Now we can clearly see that the slope is 1/2 and the y-intercept is negative 5 over 2. Next, we will graph each of these functions. So in the first function, the y-intercept is 5 and the slope is 2. That means from this point we will move 2 units up and 1 to the right and have another point. Now we will connect these points and get the graph. Now let's graph the second function. The y-intercept is negative 5 over 2, which is negative 2.5. The slope is 1 over 2, and this means that from this point we will move 1 unit up and 2 units to the right. And here we will have the second point. Now let's connect these 2 points as well. So here we have both graphs, and now let's graph the line y equals x. A few points of this line are 0, 0, 1, 1, 2, 2, 3, 3, and so on. Now let's connect these points and we will get the graph of y equals x. Do you see now how these two graphs are symmetric about this line? If on one of the lines we have the point 0, 5, then across we will have the point 5, 0. And if on one line we have the point 2, negative 1.5, then across we will have the point negative 1.5, 2. So, as you see, to get a point on the other line, we have to interchange x and y. What we know by now is that to get an inverse function, we have to interchange x and y. Also, we know that inverse functions have this property that if you perform the composition either way, you will get x. We also know that inverse functions are symmetric with respect to the line y equals x. But do you know that not all the functions have inverse functions? To understand this concept, let's talk about one-to-one functions. A function f is one-to-one on a domain D if each value of f of x corresponds to exactly one value of x in D. To understand this definition, let's consider the example y equals x to the second power. For this function, we will create a table of values, then we will graph it. In this table, for x, I chose the values -3, -2, -1, 0, 1, 2, and 3. Then I will replace each of these numbers in the function to find the value of y. Then we will get 9, 4, 1, 0, 1, 4, and 9. And we know that this equation is a function because for each value of x, we get only one value of y. In other words, each time we replace x with a number, we get only one answer. But now, let's see if the opposite is true. For each value of y, do we get only one value of x? Let's look at this table. When the value of y is 9, we have two values for x, and that is 3 or -3. The same happens when the value of y is 4. 4 has two answers in the domain, 2 and -2. And because of this, this function is not a one-to-one function. If we look at the definition says that a function f is one-to-one on a domain D if each value of f of x corresponds to exactly one value of x. And to make it even easier, once we see in the range numbers that repeat, then the function is not going to be a one-to-one function. And you know what this means for us? If a function is not a one-to-one function, then it's not going to have an inverse function. But now, if we have the function y equals 2x plus 1, you will see that this function is a one-to-one function. Let's replace the few values that I picked for x and find the values of y. We will start with -1. 2 times -1 is -2 plus 1, -1. Then we will replace 0. 2 times 0 is 0 plus 1, 1. Then 1. 2 times 1 is 2 plus 1, 3. And then 2 times 2 is 4 plus 1, 5. In this function, as you see, there are no values in the range that repeat. Therefore, this is a one-to-one function. Now, let's make the graph of the function y equals 2x plus 1. Here I have the points, and now we will connect them. Now we have the graph, and let's also graph the equation y equals x. And because this function is a one-to-one function, we can also graph the inverse function. To get a few points on the inverse function, we can just take the points we have in the table and reverse them. For example, if this point is 2, 5, then the point on the inverse function will be 5, 2. The next one, 3, 1, and so on. I have the points in the rectangular coordinate system, and now we'll connect them to get the graph. And now, as you see, we have the graphs of two functions, and they are symmetric with respect to the line y equals x. Now, let's see if we could do the same with the function y equals x squared. This is not a one-to-one function, and remember we said that this function is not going to have an inverse. We will start the graph by using the points in the table. Here we have the points, and let's connect them to get the graph of y equals x squared. Now we have the graph, and let's also graph the equation y equals x. Now let's see what happens if we reverse these points and we make the graph that is gonna be the reflection of this graph about the line y equals x. So I will plot the points 9, 3, 4, 2, 1, 1, and so on. This is the graph we are getting. But the problem is that this graph does not represent a function anymore. Remember the vertical line test that says that if we draw a vertical line over a graph, and if that line crosses the graph in more than one point, then the graph does not represent a function. So what we have here, we have the graph of an equation that is not a function. And the conclusion here is that this function does not have an inverse function. And you know that to tell if a function has an inverse function, we have a test that is called the horizontal line test. The test tells us that if we have a graph and we draw a horizontal line over this graph, and if this line crosses the graph in more than a point, as you see in this example, the line crosses the graph in 2 points, then this function is not a one-to-one function and it's not gonna have the inverse function. But now let's look at the graph to the right. Here, if we draw a horizontal line, then this line will cross the graph only once. Therefore, this is a one-to-one function and it's gonna have an inverse. There is one more thing I wanted to add here. We said that this function is not a one-to-one function and it doesn't have the inverse. However, if we consider only part of this function, for example, the part that is defined from 0 to positive infinity, then this function has an inverse function and this is gonna be the inverse. And if we take this function defined from negative infinity to 0, this is gonna be this part, then this one is also one-to-one and the inverse is this one. Next, we will talk about logarithmic functions. So let's see the definition of a logarithmic function with base b. For any base b greater than 0 with b not equal to 1, the logarithmic function base b, denoted by y equals log base b of x, is the inverse of the exponential function y equals b to the power of x. The inverse of the natural exponential function with base b equal e is the natural logarithm function denoted by y equals natural logarithm of x. First of all, we need to understand that logarithm means exponent. Let's consider the following expression. 3 to the power of 2 equals 9. Number 3 represents the base, 2 represents the exponent, and 9 represents the result. So if on the left side we are given the base and the exponent, then on the right side we have to find the result. But what if we would have the base, the result, and we would have to find the exponent? This is how we would write it. Log, the base is 3, the result is 9, and the exponent is 2. As we see here, the logarithm gives us the exponent that we have to apply on the base to get the result. In other words, 3 to the second power makes 9. The definition above tells us that the logarithmic function is the inverse of the exponential function. So let's say we have the exponential function f of x equals b to the power of x. To get the inverse function, first we will replace f of x with y, and we will have y equals b to x. And now we need to interchange x and y. That will give us x equals b to the power of y. This is the inverse function, and to solve it for y, we will use the logarithm. We will say that y equals log base b of x. In other words, if we have the base b and we raise it to exponent y, we will get the result x. Just like with the exponential functions, the logarithmic functions have to have the base be greater than 0, and this base cannot be equal to 1. Now let's talk about two special bases. One of these logarithms is the natural logarithm, and the base will be e, and another one is the common logarithm, and the base will be 10. These two types of logarithms have a lot of applications in real world. With the natural logarithms, if we have a logarithm where the base is e of a certain number x, then we have a special notation, and instead we just write ln x, that is natural logarithm of x. So when we see ln, that means that we have a logarithm where the base is e, and e is a number that is, with approximation, 2.7. Now, when we have a logarithm where the base is 10 of a certain number x, then we write this as just log x. So when we see no base here, we need to remember that this means that the base is 10. Now let's talk about logarithm rules. You may recall these rules from a previous math class. The first one is the logarithm of the product x and y equals the sum of two logarithms, that is log base b of x plus log base b of y. The second one is the logarithm of the quotient x over y equals the difference of these two logarithms, that is log base b of x minus log base b of y. So a product converts into addition and a quotient into a difference. The next one is log base b of x to the power of z equals z log base b of x. As you see, this exponent z comes in front of the logarithm, and this is what we get. The next one is log base b of b equals 1. Indeed, if we take the base b and we raise it to the power of 1, the result will be still b. In the next one, we have that b to the power of logarithm base b of x equals x. Let me show you an example here. Let's say we have 3 to the power of log base 3 of 9 equals 9. Let's evaluate this logarithm that we see in the exponent. What is log base 3 of 9? In other words, what is the exponent we will use for 3 to get 9? That is going to be 2. So if all this equals 2, then 3 to the power of 2 will give us 9. And the last rule we have here is log base b of b to the power of x equals x. Let's have an example here. Log base 4 of 4 to the power of 2 equals 2. So the base is 4, the exponent is 2, and the result is 4 to the power of 2. Indeed, 4 to the power of 2 equals 4 to the power of 2. Now let's do a few examples from page 36. Here we will do the exercise 41, and we have to solve the equation log base 10 of x equals 3. To solve this equation, we will convert it in exponential form. We have base 10, we have to raise it to exponent 3, and we will get the result x. So x equals 10 to the power of 3, which makes 1000. Now we will do exercise 47 on page 36. Here we are given that log base b of x equals 0.36 and log base b of y equals 0.56. We will find log base b of x over y. So as you see, we are given individual logarithms, but here we have the logarithm of a quotient. Therefore, we will apply this rule where we can write the logarithm of a quotient as a difference of two individual logarithms. So then, all this equals to log base b of x minus log base b of y. And now we can replace. Log base b of x we will replace with 0.36, log base b of y 0.56, and the difference will be negative 0.2. Next, we will do the exercise 55 on page 36. Here we have to solve the equation 3 to the power of 3x minus 4 equals 15. This is an exponential equation, and we have to find x. So let's see, 3 to what power gives us 15? If this would be number 9, things would be easier because we would know that 3 to the power of 2 gives us 9. In fact, let me show you how we would solve this equation if the right side would be 9. So we would have 3 to the power of 3x minus 4 equals 9. Then we would keep the left side as 3 to the power of 3x minus 4, and we would write 9 as 3 to the power of 2. And now, if on both sides of this equation the bases are the same, we can make the exponents equal. We can say that 3x minus 4 equals 2. So let's write that 3x minus 4 equals 2, and we will solve for x. We will add 4 on both sides. We will have that 3x equals 6. We will divide both sides by 3, and x will be equal to 2. And indeed, 3 times 2 makes 6, 6 minus 4 makes 2, and 3 to the power of 2 makes 9. Now let's see how we can solve the equation we have on the left side. To solve for x, we will need to take both sides under the logarithm. And we can use any base we would like. I will use the natural logarithm on both sides. So we will have natural logarithm of 3 to the power of 3x minus 4 equals natural logarithm of 15. Now this will allow us to take this exponent and move it in front of the logarithm. Then we will have 3x minus 4 times natural logarithm of 3 equals natural logarithm of 15. Let's distribute natural logarithm of 3. And we will have x times 3 natural logarithm of 3 minus 4 natural logarithm of 3 equals natural logarithm of 15. We will add 4 natural logarithm of 3 to the right side, so we will have x times 3 natural logarithm of 3 equals natural logarithm of 15 plus 4 natural logarithm of 3. Then we will divide both sides by 3 natural logarithm of 3. On the left side they will cancel, and we will get that x equals natural logarithm of 15 plus 4 natural logarithm of 3 over 3 natural logarithm of 3. From here we could simplify more if we wanted. For example, we could write natural logarithm of 15 as natural logarithm of 5 plus natural logarithm of 3, and then natural logarithm of 3 will be added to this one. Or we could just leave the answer as it is. This is an exact value, and if we would want an approximate answer, we would use the calculator. This was the last exercise of section 1.3, Inverse exponential and logarithmic functions. Thank you.